Good day. Welcome once again to our mathematics session. Over the last few weeks, we have covered some very interesting concepts as far as calculus is concerned. We started with calculus as the first branch of elementary and secondary school level mathematics that we will be considering. Of course, we still have other branches like algebra, like calculus, like statistics, like logic that we'll talk about. But we started with calculus and we have moved quite deeply into the concept of differentiation in calculus. So we looked at differentiation, what it means. We also looked at the concept of first principle and how you can use the first principle towards calculating the basic standards you have for differentiation. So we also moved on last week into the concept of product rule, quotient rule, as well as the chain rule, which you can also call functions of functions. Now, do not forget that all of these concepts are a very large array of theoretical um, subjects, right? They are basically theoretical based, and the most important thing is how you are able to apply it. For instance, if we are told that y is equal to ax per n, then what we have learned tells us that the differentiation will simply be nax per n minus 1. Standard, right? And we have also looked at ways in which this has been gotten as the answer by first principle. We have also looked at the different ways in which we can tackle questions of this forms. In fact, if we have functions multiplying another kind of function, then we would have product rule, and we can express the results simply by u dv dx plus v du dx. And then we can solve for the result of that function. Similarly, if we have a division of terms, then we can generate the differentiation with this formula, which of course we have also used extensively. And what's the major thing we also found out? We also found out the fact that not all questions will be given to you as a fraction, right? Sometimes the question will be given to you in its product form. So you could, of course, use product rule for it, but then you can also decide to convert it into its fraction. For instance, this x divided by cos x, right? I can decide to write it as x sec x, right? So instead of writing as x divided by cos x, I could write it as x sec x, and this will still give me the same value. So here, with this one, I could decide to solve it by product rule, and then if I write it in this form, I can always solve by quotient rule. What this shows you first and foremost is that the method is just a means to an end, right? The result is what matters. So however you decide to solve it is based on, number one, the mastery of the methods, the one you feel is going to lead you to the answer fast, and then the one you are very efficient with. Remember, it's not just enough for you to solve question. You also must be able to solve that question as effectively as possible. For today's session, our focus will now be on all of those theoretical concepts we have talked about under differentiation. How exactly do they apply in the real sense of the word, right? In the real world, or in other branches of science, how exactly can we use this concept? So today our focus will be on various applications we can have for differentiation. So we'll take a few of them and look at how exactly we can utilize this concept of differentiation and all the formulas and modalities we have created for differentiation, and how we can use it in a whole host of other fields, right? The very first thing is differentiation plays a very important role in the concepts of mechanics, which falls under the subject physics, right? Physics is a branch of science that is majorly concerned with the practical nature of science, and by extension, it is always going to be concerned with the smaller changes that happens between that entity and its newer form, right? Remember, we have said the differentiation is simply the, the change in that variable, the slightest change in that variable based on its independent variable. And those are changes in which physics would like to watch out for and check for and study. So differentiation plays a very, very huge role in the subject of physics or in the study of physics. Now we'll look at some of these concepts as they apply to differentiation. The very first thing is we do look at it in the study of gradients of different forms, right? Gradient is a very, very familiar term for us, especially for those of you that have gone through physics practicals and you have gone through the stage of gathering your findings, your research samples, and you have put them in a table. And then the next thing for you to do is to plot the values on a graph. And then when you plot your values on a graph, you'll be asked to find the gradient of that graph or the slope of that graph. What you simply call the gradient or the slope is in fact the y, the x. This is simply what you call the gradient or slope. Now let's link it up with what you are familiar with. Do not forget that for your gradient or slope, you would say you have it as y2 minus y1 divided by x2 minus x1, right? What you have essentially done is you have measured the change from y1 to y2, and then you are also measuring the change from x1 to x2, right? And the change of y is dependent on the change that happens on x, because if you draw your graph, right, if you pick your x values here, your y values are on the y-axis, obviously. Every x value you pick determines what the y value will be, and based on that determination, you can draw yourself a straight line and then calculate the gradient across that straight line. So you see that it still boils down to the basic definition of differentiation, which is the slightest change in y with respect to x. And that's why, if you remember clearly in your physics graph, physics experiment, they will tell you that for your gradient, it doesn't matter if you pick a very big triangle or you pick a very small triangle. It does not matter at all, because the gradient you will get for any of the triangles you pick will be the same, right? Because what that is saying is it doesn't matter whether you consider a very large change or you consider a very, very small change. Your gradient value, which is the dy dx, which is the differentiation, remains a uniform value or concept across your triangles, right? And essentially, what we say y2 minus y1 is simply the change in y divided by the change in x. And I'm sure these symbols reminds you of first principle. So you see that the gradient which you do in physics is still essentially utilizing the differentiation concept for mathematics, right? So essentially, it means that we can use the concept of differentiation into solving questions for physics as well as any other branch of science that utilizes slopes or gradients, and it will still bear the same fruit. So let us see what these questions look like. Let's not just see it by word of mouth. Let's see what these questions look like, and then we'll be able to generate as more other applications as we can have. So let's start with this. We have to find the gradient of the curve y equal to x squared plus 3x minus 1 at the point on it where x is equal to 3 and then x is equal to minus 2. Now, this is a very, very commonplace question. Remember that on the graph, not all your diagrams on the graph will come as straight lines, right? Of course, most of your physics graphs will come as straight lines, but some will come as curves. Some will come as curves, essentially meaning that you must be able to calculate the gradient based on a particular portion of the curve or by utilizing the tangents to the curve, depending on however the question is given. In this case, you have to find the gradient of the curve at the point on it where x is equal to 3, x is equal to minus 2. So the very first thing is, let us find the gradient representation, impute the value of x, that will be the second step, and then we will have the gradient to seek. So let's start. The very first thing is, since y is equal to x squared plus 3x minus 1, the very first thing to do is to differentiate. That is the advantage of the concept of differentiation. Whereby before I would be thinking of, okay, let me find a range of value for x that contains these 2 points, let's say for minus 4 to 4, and then let me plot this curve on a graph, and then let me start picking these values of the curve and try to form a particular triangle. All of that would have been so much complicated. But by the concept of differentiation, I can simply just pick the equation of the curve and just differentiate. So I'll have dy dx will be equal to 2x plus 3. So if dy dx is equal to 2x plus 3, all I'll just do is to find the gradient values at each individual point. Now, at x equals to 3, this is how I would denote it. Dy dx at x equal to 3 will simply mean 2 times 3 plus 3. 2 times 3 is 6 plus 3, that will give me 9. Similarly, dy dx at x equal to minus 2 will simply be 2 into minus 2 plus 3, and this should give me minus 1. So it means that my gradient value at x equals to 3 is 9, whereas my gradient value at x equals to minus 2 is minus 1. So this showcases how we utilize the concept of differentiation towards finding the gradient. Let's pick yet another example to see exactly how it works as clear as possible. Okay, so let's find the equation of the tangent to the curve y equal to x squared minus 4x plus 3 at the point 3, 1. This is the point given to us, and then we have the equation of the curve. And then we are looking for the equation of the tangent. Now, first thing is the equation of the tangent, right, for a curve shares one um, major characteristic with the equation of the curve itself. And that is the fact that both the equation of the tangent and the equation of the curve both have the gradient the same, right? The gradient of the equation of the tangent and the gradient of the curve itself are the same. So essentially, what this means is that if I can find the gradient of the curve, right, that would also be the gradient of the tangent, and then I can use that to find the equation of the tangent itself. Now, do not forget that the tangent is a straight line. The tangent is a straight line, which means that to find the equation of a straight line, which in this case is the tangent, I can just utilize the gradient and 1 point form of finding that. By the time we deal with circles and straight lines later on in our classes. We will go deeper into that. Don't forget that this is all about applications of differential, which is where exactly can we use differentiation. So let's start with the equation of the curve, x squared minus 4x plus 3. So I will differentiate this. If I do, I would have us to be 2x minus 4. So if it's 2x minus 4, then the gradient at x equal to 3. Why am I thinking x equal to 3? Because I'm thinking at the point 3, 1. So it means x is 3, y is 1 at that point. I don't know if y in this equation. So I use x equal to 3. And that will give me 2 times 3 minus 4. That will give me 2. So it means that the gradient at the point 3, 1 is 2. Right? So I have a gradient and I also have a coordinate. So I can use gradient on 1 point form. So thus, the equation of the tangent is, of course, by gradient at 1 point from y minus y1 divided by x minus y1 is equal to the y dx. Normally you see it as m because that's how we represent the gradient, but you can also represent it as the y dx because that is how we got the gradient in this case. So that will simply be y minus 1 divided by x minus 3 equals to, so this means that y minus 1 is equal to 2 into x minus 3. So y minus 1 is equal to 2x minus 6. So we can go for that to make y subject of the formula. So that means that y is equal to 2x minus 5. So what this means is that the equation of the tangent, which is of course a straight line, is y equal to 2x minus 5. And if you compare it to y equal to mx plus c, see that m, which is equal to 2, is in fact the gradient. So this makes a whole lot of sense as far as utilizing the concepts of differentiation into gradients and the basic or various concepts that revolve around gradients, right? This is very, very interesting. Now that we have this, let us look at, of course, gradients are not the only way in which we can apply differentiation. It's not. We can also apply differentiation in a field that is, in fact, very, very commonplace to us as science students, and that is the concept of motion. Motion. Now, this is also a mechanics concept from physics. In motion, particularly velocity, accelerations, these are concepts that totally rely on differentiation. Now, before we go deeper into the concept of motion, we have to first and foremost introduce ourselves to what we call higher derivatives. Higher derivatives. Now, we have looked at the fact that if y is equal to a function, then the y dx is simply the differentiation of that function, right? We call this dy dx the first derivative in English. What is the first derivative? Or you can also see it called the first differential, as the case might be. Now, first meaning that there are still loads of other differentials that can happen beyond it, right? We call all of those higher derivatives. We have the second differential as d squared y over dx squared, which simply means that differentiate after you have differentiated. So after you have gotten your first differential, differentiate it again. That's why we call it the second differential or the second derivative, right? So the continuous differentiation of a particular function gives you the continuous derivatives on that function till that function gets to 0, right? So the moment the function gets to 0, that means you can no longer differentiate them, because if you continue differentiating 0, you will get 0. So there's no change at that point. Similarly, if you have the third differential, It simply means differentiate the second differential again, which is simply you differentiating the differential of the first derivative. That's pretty much how it works. So you call this the third derivative, and so on and so forth, right? So notice the position of the number. In general, we have the ny over the x raised by n, which we call the nth derivative. So notice the position. The d on top carries the power, the x below carries power. So this is telling you the nth difference, right? Or the n changes, the continuous changes on y, which is occurring because of the continuous changes on x, right? The nth derivative or the nth differential. So these are what we refer to as higher derivatives. Let's take a quick example. For instance, if y is equal to 2x raised to power 8, for instance, then the first differential by our standard form will be 8 times 2, 16, x raised by 8 minus 1, 7. And then you can differentiate this 16x raised by 7 again to get the second differential. So for the second differential of 2x raised by 8, all you just have to do is this first differential, which is 16x raised by 7 that you have gotten, differentiate it again. So that will simply be 7 times 16 x raised to power 7 minus 1. The same process, but this time on the first differential in order to get the second differential. So that is how the process continues. And then here you have 112x raised to power 6. And again, you can take this process and continue to interpolate on it, which is from here I can calculate the third differential, which is just going to be the differentiation of 112 x raised power 6, which is the second differential. And if I differentiate this will be 6 times 112 x raised power 6 minus 1, right? And if I differentiate this, you see how the value continues to increase. So in this case, I will have myself 672 x raised to power 5. And again, it continues. It continues on and on and on. So from here, I can move on to say, okay, I want to find the fourth differential, fifth differential, sixth differential. That is what higher derivatives are all about. Now, you can utilize the concept of higher derivatives into motion, particularly velocity and acceleration of a moving object. Now, in physics, we particularly discuss the concept of scalars and vectors. We say scalars have magnitude, no direction. We have vectors that have magnitude and direction. Essentially, when we talk about motion, we want to consider those entities that have both magnitude and direction. So we're talking about displacement, velocity, as well as acceleration. Now, this concept of displacement, velocity, and acceleration, there is one key independent variable that holds all of these three concepts together, and that's the variable of time, right? You measure your displacement based on time it takes you to cover that particular distance, right? So if I tell you that my displacement is 5 meters, for instance, I am representing that 5 meters